All right, guys, we're going to go ahead and get started with class. Today we're going to finally talk about this thing called the derivative, which I've alluded to a little bit throughout this first unit. Some things going on this week. I did just want to remind you that you do have your test on Friday. Between now and then, so today we're doing notes. Tomorrow I have notes, kind of finishing up the introduction to this thing called the derivative. Wednesday and Thursday are going to be work days for you finish homework, ask questions, work on your briefcase binder, and then your test is going to be on Friday in a similar format of the quiz. So looking at our notes today, we're again are looking at this thing called the definition of the derivative.
Mr. Brown, I don't see the notes yet on my side. I got like 01 notes.
I'll look, because I shared them like 2 weeks ago, so it shouldn't be a syncing issue. If you don't see them, just take notes on a sheet of paper, but I'm going to see if I can get them there. But we're going to be looking at the derivative, and I guess give me 1 second to fix this.
Mr. Brown.
Yeah.
While you do that, how many tests can we have in a day?
How many? Teachers are still supposed to be following the certain
2,
testing
right?
days. And math tests will be Wednesday and Friday.
Yeah, I have 3 tests that day.
What other subject do you have tested, if you don't mind sharing with me?
Yeah, AP Physics C, and then half of AP Micro.
Yeah, so I think Friday also has science. Micro is probably the one on the wrong day.
Okay.
But they might justify it since it's the second half of the test. But technically, that's just math and science day.
Yeah, that's what I thought. I thought it was just math and science. Yeah. All right. Thank you.
I'll let Dr. Shaw I'll tell Dr. Shaw to send out an email to remind just teachers of that.
Mm-hmm. Thank you.
You're welcome. Oh, it looks like because I named it the wrong file, guys. If you're still trying to find the notes, the title of it is How Can I Analyze a Function's First Derivative Graphically? That's my fault. Looks like I just renamed the page. It looks like it's the 3rd page under notes. So we're looking at this thing called the derivative. I did want to kind of review on some like prereq stuff that I think you know, maybe not know, but at least attach it to some words from geometry that you know actually, and then expand it from there. So, not that big. The first thing I want to talk about is this thing called the secant and tangent. I think you know those words from geometry. In geometry, the secant is a line that touches a circle 2 times, and then we know the tangent is just a line that touches a circle at 1 point. We can expand that definition to be with just general functions. A secant line is going to hit a graph twice, or it's going to be mainly defined by a graph by 2 points. So it might intersect a few more times if the graph bends a certain way, but it's going to be created by 2 points. And the most important thing about a secant is it is associated with the average rate of change. And oftentimes we just call that the slope, which you've been talking about since, I don't know, the 6th grade. And so like if I wanted to find the slope of that line, we know we basically do the change in y over the change in x. And that's kind of what we're going to call a secant line. It's going to be a line that connects 2 points in the function. Whereas the tangent line is like a circle, only going to touch the function in 1 point unless the function bends and crosses it again. Instead of being associated with the average rate of change, we associate it with the instantaneous rate of change. And that's really what calculus is going to be focused on. So like we will see the secant line sometimes, but in calculus, we're talking about the tangent line. Because what's going to be unique about calculus is we're actually going to be able to find what the slope of the tangent line is. And that is a question that calculus is often answering because that actually has lots of different applications. There's like direct ones like associating with physics, position, velocity, acceleration, to other applications like talking about minimizing and maximizing situations, and everything else. Like we really will be looking at the derivative between now and November, basically looking at like what the derivative is and then the different contexts that this derivative exists in. So I did want to go ahead and give you the definition that we're going to use for like what a derivative is. And so the meaning of the derivative and kind of its concept and the way I want you to think of a derivative is the derivative of a function f at c is the slope of the tangent line at x is equal to c. And that's really what I want you to kind of associate in your head is that when I say the word derivative at x equals c, that is the slope at x is equal to c. So the derivative is literally a slope, but instead of being a slope defined by 2 points, it is a slope defined by a single point. Oftentimes the derivative can be thought of as well as the instantaneous rate of change at that value. And so to take you back to the graph that we did above it, I won't go too far up so you can still see the definition if you're writing it down. But when we're looking at the tangent line, when we see what is the slope of the tangent is literally equal to the derivative. And so we do want to have some notation. We know math has plenty of different types of notations that we can use. And when it comes to the derivative, we really do have 3 types of notation that I want you to be familiar with. We have the Lagrange notation, the Leibniz notation, and the Newton notation. These are all mathematicians. They're all kind of credited with making advances in terms of calculus. Leibniz was a German mathematician. Newton, that is the same Newton as in Sir Isaac Newton and gravity. And then we also have Lagrange. But their notation is what's important to know. I'm going to do the Lagrange notation first. For the Lagrange notation, we're going to write it as a fraction with the lowercase letters dy, and then it's over dx. How you literally read this, like even though it's written as a fraction, you literally read it as dy dx. So I'll say like dy dx at 3, dy dx at 4, and that just means the derivative. We also have Leibniz notation. His notation is going to use apostrophes to represent the derivative, and you would read that out loud as like f prime. So when I say f prime, I'm talking about the derivative. Newton is not as important. So like BC calculus and most textbooks only use Lagrangian notation and Leibniz notation. But just to give it to you, Newtonian notation is just a y, and he used a dot instead of a prime. And the reason why we have so many different ways to write this notation is calculus kind of developed in different areas at around the same time. So like different areas had their own notation. And now in the modern world, we just kind of have 3 different notations. But Lagrangian and Leibniz are the ones that we mainly see. Oftentimes, we're going to be talking about the derivative at a point. So like if I wanted to write, like say, f prime of 2, that statement literally means what is the derivative at 2? Kind of like when if I say f of x, that means what is the value of the function at x. F prime of 2 means what is the value of the function at 2. Lagrangian's notation is not as friendly to write when you're plugging in values, so we still write dy dx, a vertical bar, and then the x value that you're plugging in. But we do kind of need to easily switch back and forth between Lagrangian notation and the Leibniz notation. So let's kind of talk about the limit definition of the derivative. So the whole reason why we really learn limits is so that we understand where this derivative is coming from. So before I give you the definition, I'm going to kind of go off to the side, and I want you to just kind of sit back and like watch me do some things, and we'll kind of talk about it. So I'm just going to draw a generic x and y axis, and I'm going to draw a generic function, and I'm going to just call that function f of x. And when I have that function, we know that we can just take any 2 points, and if I connect those points together, that would be a secant line. So there's my secant line. And we know that that secant line has a slope. Like we could find that slope if we knew those x values. We could do like change in y over the change in x. In calculus, what's going to be important is not really the secant line, but if you have a point, if you can find the actual slope at that point. So the green one is going to be my tangent line. And the question that calculus is going to kind of answer for us is, what is the slope of the tangent line at a particular y value? And limits allow us to kind of answer that question. So let's say this is my function, and I'm just going to pick a random x value. I'm going to say that this x value is 2. And so if I say what is the slope of the tangent, that's literally me asking what is f prime of 2. What is the slope at 2 is the same thing as saying what is the derivative at 2. And the idea behind where the derivative comes about is if you have the secant line, I'm going to name this other point here, I'm just going to call it x for now. And you're going to imagine, I'm going to send it out through a mind at the end of the day so you have time to kind of play around with it. But I want to introduce it first myself. But what you're going to imagine is this point I labeled x is going to move closer and closer to the other point. So close, in fact, that that point is going to land on top of the other point of the secant line. Well, once those 2 points merge together, some of you might be able to visualize it a little bit better. But when those 2 points eventually merge together and form the same point, we're basically changing that secant line into a tangent line. Well, we do have something in math that lets a point approach another point, and that's going to be a limit. So we are basically literally letting, in this case, we're letting this x coordinate approach the value of 2. And when that happens, we are going to be creating a tangent line. How can I put all that stuff into notation? And then I'll kind of open it up for questions. So we do have 2 definitions for the limit. I went ahead and just called this f prime of 2. So in words, this is basically the derivative at 2. Which we know the derivative is the slope of the tangent line at x is equal to 2. And we have 2 definitions. I have what's called the alternate definition and the traditional. I know it looks a little bit weird to have the alternate one come first, but to me that's the easier one to understand. And you'll actually recognize some of these limit statements in that you've technically already found derivatives before without even probably not knowing you were finding a derivative. And so the alternate definition is going to be the limit as x approaches the value that you're approaching the limit at. And then it's basically the limit of your slope formula. So the slope formula had the change in y minus the change in over the change in x. So I have the change in y over the change in x. So in this formula, things that I want you to gain from this for now, this part is just your old school slope formula. That is a change in y over the change in x. And with the limit in front of it, you're basically making the 2 points of a secant line join together and they become a tangent. The traditional definition is going to be the limit as h goes to 0. These are going to be our plus h problems. So I have f of, we're taking the derivative at 2 plus h minus f of 2. Where this formula comes from is that if I went to that same diagram and I wanted to find the tangent line, h would be the distance between the two x values, whereas that distance goes to 0, those 2 points would end up merging together. So h is going to 0, so those 2 points would merge. When those points merge, instead of having a secant line, we now have a tangent line. Last thing I want you to get is that these 3 things I wrote in that box are all equivalent. F prime of 2 is exactly the same thing as saying this limit expression, the alternate one, which means exactly the same thing as the traditional. I could have also written this in the Leibniz notation and written it as dy dx with the vertical line at x is equal to 2. I just threw a whole bunch of calculus theory at you, but are there any questions that you can formulate so far? And it's okay if it doesn't quite click yet, I promise you it will. All right, so let's go ahead and talk about why this thing is important. So the notation is important, but really what's most important to us right now is like, well, what does this derivative actually help us do? So in its most basic form, the derivative can tell us about how a function looks and how a function acts. So if you look in this box on here, we're going to talk about the cases where the derivative is positive, the derivative is negative, the derivative is 0, and then that fourth column just meaning what does it mean if the derivative is not defined. So to help you think about this, again, when I say derivative, what are you associating the derivative with in your head? Or I'll ask it this way, what should the derivative represent?
The slope.
Tangent
It's the
line.
slope. So like in its most basic form, don't overcomplicate it. Just think derivative is slope. Derivative is slope. It's a different kind of slope. Instead of having 2 points, it's at 1 point, but it's still a slope. So in this first statement where it says f prime of c is positive, I can also just reword that as saying at c, the slope is positive. Well, what would your graph be doing if it had a positive slope?
Approaching infinity?
It would be approaching infinity, just be even more basic. Talk in terms of middle school math. If you had a positive slope, what would your line be
Goes
doing?
up.
It's
It
going
goes up.
It goes
It's
up.
going up. So that's all we should think of. Like calculus is just 6th grade math in different names, in many ways. Not quite, but kind of. So when I see f prime of c is positive, this literally means that f is increasing at x is equal to c. Both of those statements are interchangeable. Careful with your words, like I didn't say f prime is increasing, that means something else. So when f prime is positive, that means f is increasing. So you can kind of conclude from there, and I'll do the examples last. If I say f prime is negative, what do you think your graph is doing?
Decreasing.
It is decreasing. And it is important because now we're no longer dealing with straight lines. So it's just like at that moment, at that split second, the graph is increasing or decreasing. And then when f prime is equal to 0, we're simply going to state that f is neither increasing nor decreasing. So basically it's not doing either of those. It can't be going up, it can't be going down. So either it's going to be completely horizontal or just horizontal for that exact moment. So let me be a little bit more clear here. At x is equal to c. So before we look at the cases where it's not defined, let's make sure all this is clicking. So at the bottom, I have some graphs, and I want you to see if you can figure out an x value that would have that description. For example, in this first one, I have f prime of something is greater than 0. What would be an x value that would have a derivative that's greater than 0 for this particular graph?
4.
4, that's an easy one to see. 4 is on an increasing section of the graph. You can even draw the tangent line. There's the slope of that line would represent the derivative. So f prime of 4 would be greater than 0. Moving across, what would be a derivative? What will be an x value where the derivative is less than 0?
1.
2.
2, 1, pretty much anything along this decreasing section. 2 looks like a good one to choose. There's the tangent. Again, the derivative is not the tangent. The derivative is the slope of the tangent. So f prime of 2 would be less than 0. What about this last one? What will be an x value that has a derivative of 0?
3.
Either 3 or 5.
3 and 5. The easiest way to tell that a derivative is equal to 0 is it has a horizontal tangent. And I might make a note of that for when the derivative is equal to 0. Just because that's a good way to describe it. We know it's equal to 0 there because we have a horizontal tangent line. And we know that kind of makes sense because what's the slope of a horizontal line?
0.
0. And that's what the derivative really is representing. And then the last kind of concept is, unfortunately, sometimes we don't have a derivative. And there's 3 main cases you need to know where the derivative is not going to be defined for BC calculus. There are a few other ones that are a little bit more complex, but they don't show up in BC. And the 3 cases you need to know is discontinuity. If your graph has any type of discontinuity, there's not a derivative at that x value. So it can have a derivative everywhere else, but at that x value, it cannot have a derivative. So we say like the derivative is not defined. So any discontinuity, of course, includes jumps and vertical asymptotes, but then also holes. So none of those cases will ever have a derivative at that x value. And those can look, the jumps can either have an open or filled in circle, still no slope there. Vertical asymptote, of course, no slope there. And you can't have a slope if the point is not even there. The other case where a derivative does not exist is when you have different left and right tangent lines. And graphs that would not have a derivative because they have different left and right tangent lines, the easiest one to visualize is an absolute value function. Another one is, this is x to the 2/3. It makes like that bird shape everyone drew in elementary school. For those graphs, at this little corner, there is no derivative. So there is a derivative everywhere else, but not at that little corner. The mathematical name for it is called a cusp. But corner is also acceptable. In fact, I have seen the word corner used on the AP exam multiple choice questions before. Cusp is more common, but they really are going to be interchangeable. So if you have a corner or a cusp, there is no derivative there. And then you also will not have a derivative at a vertical tangent line. So like if I have, this is a cube root function. At this value right here, you have a vertical tangent. Well, in math, what do we say the slope of a vertical line is?
Undefined.
Undefined. Well, if the slope is undefined, then the derivative does not exist, which is kind of easy to remember. So those are the cases that we have for the derivative. And on the next page, we have some examples that we're going to kind of look at. But that's really the concept stuff I want you to understand today. Anything on that in that box I can go back and explain a little bit better? All right, so go ahead and go to the next page. This is really only 4 problems. You have your homework for tonight is very similar to this example, which is why I want to do some of her notes. And how this assignment works is I have one graph, and I'm going to say that that is the graph of f. And I have 4 different statements in kind of like the first column in bold. The second column, only one of those meanings fits the mathematical statement written down. So I want us to be able to figure out like which math symbols goes with which statement, and then determine whether it's going to be a positive value, a negative value, 0, or not defined. So for this first one, I have f of 3 is equal, not f3 is equal to f of negative 3. Does f of negative 3 represent the y value, the slope of the secant line, or the slope of the tangent line? If I just told you, hey, what's f of negative 3? What would that represent?
The y value.
That's just the y value. So that's not calculus. We know that that's the y value. So I'm going to go ahead and put a dot there. That is f of negative 3. There's my point. Would you say the value of f of negative 3 is positive, negative, 0, or not defined based off of that graph?
0.
0. If it was above the y-axis, positive. If it's below the y-axis, negative. If it was a whole, not defined. But clearly, f of negative 3 is 0. Let's look at the next one. I have this statement, f of 1 minus f of negative 2 all over 1 minus negative 2. Of those 3 statements, which one is going to go with that one? Is it going to be the y value, slope of the secant line, or slope of the tangent line? Anyone want to take a guess?
Slope of the tangent line?
So it does definitely represent a slope. I want you to maybe adjust your answer. Look at that question and the one underneath it as I zoom out too far. Which one of those, if you're looking at the second and third question, which one will represent the tangent and which one will represent the secant, and how can you tell?
The top one is the secant one.
So the first one is the secant. Let me get the highlighter. The first one is the secant, and kind of here's the clue how I can tell. 2 reasons I can tell. I know that that one's going to be the secant because it has 2 different x values, and we know the secant line is going to connect 2 x values. There's also no limit in front of it, so we're not like limiting this down to just 1 point. So this would be the secant line. Basically, it's the secant line from -2 to +1. And then you can go in the graph and draw in a secant line from -2 to 1 to determine whether it's positive, negative, 0, or not defined. So again, my secant from -2 to 1. Here's the point at -2. Here's the point at 1. There's my secant line. So would that value of the slope be positive, negative, 0, or not defined?
Negative.
Negative, and we know that it's negative because it is decreasing. So then these last 2, we can probably assume we already mentioned it vaguely. Both of these are derivative statements because we do see the limit there. That's kind of your clue. So this is representing the slope of a tangent line for both of them. Other ways we could have written this one. So I see that this first one is the limit as x goes to 2. I could have written this simply as f prime of 2. Both of those statements are interchangeable. Obviously, writing f prime 2 is a lot shorter. I just need you to understand the limit format of it as well, or at least be able to recognize it is what's important. This second one, I see 3 as a value in there. So I could have also written it, this bottom one, as f prime of 3. I could have also translated both of those from like the alternate to the traditional. For example, right now, the one with 2 in it, this is the alternate definition. If I wanted to translate it into the traditional definition of the derivative, we would use as h goes to 0. And I would plug in, so this was at 2. and it would look something like this. So that statement I just wrote down is equivalent to the limit statement that's typed in, which is equivalent to just saying f prime of 2. Looking at my graph, so going up to where x is equal to 2 at, here's 2. So here's me estimating the tangent line. Looking at the tangent line, would you estimate the derivative to be positive, negative, 0, or not defined?
Negative.
Negative.
Negative. So we know that that one would also be negative. If it asks for a reason, it would be because the tangent line is decreasing. Notice I was careful with my language. I didn't say like because it is decreasing or because the derivative is decreasing. Nope, it's because the tangent itself is decreasing. And then this last one was the limit with 3 in it. So we knew that this meant the derivative at 3. What are we saying the derivative at 3 is going to be? Positive, negative, 0, or not defined.
0.
So let's look at it closely. Do we see a smooth or a sharp turn?
Sharp.
Sharp.
Oh,
Sharp turn. So anytime you see a sharp turn, again, we're going to call that a cusp or a corner, and the derivative would not be defined. So for this last one at 3, we're going to say it's not defined because there is a cusp there. I do want to make sure it's kind of clear the difference between a derivative being 0 and not defined. Looking at this same graph, so we just said that f prime of 3 is undefined because we had a cusp. Where on that graph would the derivative be equal to 0?
-1.
-1. So the derivative would be equal to 0, -1, because we do have a horizontal tangent. We can draw it in on the graph there. Any questions or things I can clear up?
I have a question about homework.
Uh-huh.
So, there's like a homework 5 in OneNote, but you said we don't like that. There is no homework 5. So does that mean it's just optional?
I just would not worry about it for right now.
Okay.
Like if you want to do it, you can. Like I am going to assign it just in a different unit. And the issue is like I had created the assignment at the beginning of the semester, but even though I deleted it from Teams, obviously since it's sent out in OneNote, it doesn't, like I can't undistribute once it's in your OneNote. So just kind of ignore it for now. You can also delete it if you want, if it gets in the way. But that's where I'm going to finish these notes today. Like I do have a second day of just this very, very introduction to the derivative. So your homework, again, there is a new worksheet. It honestly shouldn't take you very long. It's almost just like that second page of notes with just more questions. Of course, work on homework number 4, continuity, if you haven't already. Again, tomorrow we'll have some notes and another like short homework assignment. Homework number 7 is actually only 1 page long, so there isn't a front or a back to it in your OneNote. Wednesday and Thursday are review days and a time for you to use class time to study, work on homework, and prepare. So don't think you have to do all of this tonight. Definitely meet with me during office hours if you feel like you're falling behind or if you wanted to ask any specific questions on your quiz. But other than that, I know I'm cutting it close to when the bell's ringing. There is about 5 minutes left of class. If you're good to go, you can go ahead and sign out, and I will see you tomorrow. If you wanted to hang back and ask any questions, you're more than welcome to do that as well.
Okay, Mr.
Bye.
Brown.
What's up?